Right, hello everyone. So we are doing again. We're going to split it into two parts this time. First part, we're going to finish up a little bit of our combustion theory that we didn't do last time because it was late at night. And then we're going to go to FE. So first thing we're going to do is finish up this. And then we talked about Helmholtz function and the entropy function, which I recommend you just write down. And then we have Gibbs free equation. So this is a beautiful equation over here. I don't think I talked about it last time, which is unfortunate. So Gibbs equation is this basically, and there's multiple things you can get by it, but it's again something that it's just a definition. I want you to, you know what? Uh, yeah, just think of it as a definition for now. Gibbs actually has certain meanings sometimes, which is why I'm hesitant to say that it's you can just say it as like it's a relation really for now. Let's just say that. Because I try to think in the future, is there any difference between this and a relationship? Um, I've used Gibbs a few times in my lifetime. In certain classes, the compressible and other stuff. But in reality, the entropy is king in my opinion. This one I've used multiple times. I'm still confused why they didn't use specific in this textbook, but it doesn't really matter in my opinion. So I realized last time we didn't really cover species or what phase really is and why they're important. So species, so you can think about them as different chemical types. So as you can see, you have something like this happening where you do a combustion over here and get these stuff. And obviously, they have to add up to the original 1 mole, 2 mole. And over here, you see that there is a differential over here for each one. There's like a certain differential, which is a derivative, basically, a change in whatever material you have. So here's the beauty of that. There's a negative, negative, positive, positive. It's just a showcase of that. I actually don't know. I know it works because the math works and the physics and chemistry works. I don't know how true it is, although if I were to give you this thing and tell you to like make tell myself to make a CFD of it, I wouldn't know if it would work the way I would do it. I think there are some other functions you might need, which is why I'm still reading the appendix. Now, here's the thing about phase. The liquid and gas are not the same. So the phase does matter in the regime of talking about this thing over here. So you can kind of see what's happening here. And you can see that there's a difference between NH2O and H2G. So keep that in mind when you're doing it. And they're not the same thing. They are completely different, and you need to carefully select them, figure them out, and that's what you do in this case. So yeah. And now we're talking about placeholders for extensive thermodynamic. Here's where I was wrong. Last time I said, when will you use extensive? It turns out there's a placeholder. That's why people have differentiate intensive versus extensive properties. Is because of this placeholder, which is any amount dependent property. So as you know, volume increasing the portion size matters like volume for extensive properties. So here's some example of them. And you can see we see some of the entropy and Gibbs, and we don't see Helmholtz. Okay, Helmholtz is not there, but entropy is there too. So I wasn't really quite sure about it, but it is in there. So another thing we'll just do, and for now you won't understand why we are doing the N over here. We're getting rid of all the molecular to get this. So for now, we'll claim that this is true for before reaction if composition is frozen, and after reaction if product is fixed. That's what my brain is telling me, but this could also be expanded on because what I learned later on is a lot of times by making the property dx dt zero, we have a situation like initial conditions and boundary condition where we have zero, but extrapolates more physics because what it's basically saying is that because in one location is zero, that's enough information for the rest to figure out, which is quite true in a lot of physics. I'm not sure if that's true for this case over here, which is why I'm being quiet over here. I'm just claiming what I know is probably true because I would be flamed if it didn't. I'll probably still be flamed because I'm probably wrong somewhere. But yeah, and this is apparently according to William A. Foreman's book, the Maxwell's equation, usually relationship, which I know the Maxwell's equation a long time ago when I took electricity. I did not know it comes in here, which probably means Maxwell's a famous guy. He probably created multiple things. This is probably another thing he created. I'm not sure too much, but we'll just say it like that. So over here we have our dg, which is negative s dt plus the volume and dp. So what's happening over here is that it confuses me a few times when you don't understand it. And when you understand it, it doesn't confuse you. But this is exact partial differential equation, And how did that exact differential equation formed is due to, I mean, look at this. We did a whole entire section in my textbook about it because this form over here is like how we denote it, basically. So I don't want to say go back because that's a bad way to teach you how to explain everything. The way to show this is now we're going to use is a shortcut, but it's a good shortcut in my opinion. So we know that these two are true because we have seen that's true, right? We have seen it. So we're just going to match these two for now. Match these two. Simply just do that. When you match those two, you get these relationship over here. Now, I want to take up you to make a derivative of each other. This is a classic thing that Dr. Sanchez uses all the time, where he would just pick, if you have a scalar, he would just take another derivative of the other one to make them equal to each other so they can actually combine to one equation. In this case, that's what we are gonna do. When we do that, we get this relation over here, and by mixed equal partial, we get that this is true. These must be equal, and that relationship happens. And for now, we'll say basically there's a bunch of other ones, but we'll basically say in a did I have anything over here? Chemical reaction before and after. In between, I'm not sure, probably not, because what I'm saying in that case, this term is activated. Therefore, it probably won't be in between because it makes no sense to be in between and still apply the same rules, right? If you think about it for 5 seconds, um, it doesn't make sense in my opinion. Um, Maybe later on in Foreman A. Williams' book, he will disprove me, and I'll be proven wrong. But in my brain, it doesn't make sense to when the whole thing is changing. And again, there's another thing to say. If there's another reaction over here, and this is a chain reaction, then this is no longer true too, because there's a differential at the end, which means that if there's a combustion that goes both ways and never settles, it will never be stable. So in that sense, it only if I was thinking of like a combustion, like a fire, in between there could be a multitude of things over here. So I would generally say safe outside and maybe in the fuel tank. I really don't know. The most important part about that fire is unknown. Maybe you can differentiate over here and figure something out. Oh, by the way, this is a differential, which is lovely because you can as I'll quote Dr. Sanchez, you can what did he say? Just take a dt over here. Oh, now you have a dt. You do a ds over here. Now you have a ds. Dr. Sanchez said that. I think I paraphrased it a little bit, but basically, if you have a differential like this, a dd something, you can just divide it by anything and make another differential equation. Is what I'm saying. For now. Next thing we'll do over here is inert. No, it's a claim. So here's the thing about natural ideal gas. It's not in the book, but I think it's time for me to put that down here because I've it's probably somewhere in the book and I just can't find where yet in the appendix. And it probably is going to be appearing soon. And I just said, okay, if it's going to appear soon, why not just add it now? So this is from Wikipedia over here. This is actually, I think, a bad image, but it's there. But here's the thing about Z. It's not the right way. How do I explain it? We use it. We definitely use it. It's just sometimes not right. It's hard to describe when it's not right. How to describe when it's not right. Okay, so what I'm trying to say is that, wait, did I do this wrong? I need to double check this now. But this Z over here is Z equal 1 is when ideal gas sometimes works, but that's not always the case for certain gas. Basically, what I'm trying to say is that this is for, if I remember correctly, idealized, I mean, it worked for combustion mostly. And there's a lot of assumption like low pressure, high temperature, and there's a gas phase and not close to turning back into water or liquid. Should say liquid. Um, uh, Yeah, for now we'll say that. There's probably more restrictions I'm not thinking of, but for now those are the main restriction. Low pressure, high temperature. Honestly, these you don't really think about. You just have to say it's a gas and it's very far away. Just high temperature, whatever. For now, but that's how I remember it. But sometimes I don't remember because ideal gas law you just use it no matter what, even if it's like so much error, like 15% error. Even if it's a 15% error, you would still use it because CFD is the best idealized gas, whatever. They just use it whatever whenever they feel like it. I don't really know how to like, yeah, just use it. Okay, so. Here's the most interesting thing I found so far. So we are gonna use dt and dp as 0. I mean, we can just minimize it for now. I'm not using my hands for anything. Excuse me. So over here, um, what's happening over here is this is happening. This chi is a placeholder. This chi is being used over here, and you're doing a partial differential fraction, which is basically what we learn. And in his textbook, we use dt, dp, dn. And I'm gonna quote Dr. Sanchez here. You only need 2 of the variables to figure out all the rest. So I'm pretty sure that's why this dp, dt, and dp. You could do other things, dp, dv, or whatever. You just need 2 of the state variables to figure out everything. Don't really think why, but we're going to actually change this to 0 for some reason. And then we're going to create a boundary condition like this. And then after that, we get this format over here. And with a little bit of the differentiating over here, we got this form over here. It's, again, a law of product rule. Yeah, a law of product rule. So what happens over here is that we get this differential equation, and we just say happy, happy, go lucky. No, we see that only this part over here, well, not this part, the other one. This part over here is in the equation, but the other part is mysteriously added on. And this is everything else. This is going to be our S dpt plus VDP. And you might be asking, wait a second, how can we claim that when we said the derivative is 0 and the pressure is 0? Now, I want you to remember when we did IC. When we had a differential equation, and this is how I justified it. let's just say equal 1, right? We have integral that, and we did dx dt equal what? A, right? Oh, no, no, no. Oh, x first plus a, right? Right, we did that. And we do another integral where we do x equal, oh, that's not x, sorry. This is time. And then we do another integral, and we did t square, right? Plus at plus, um, no, there's a half here, b, right? Now, if our to get a and b, we have ICs, right? Which is x0 equal 1, or we have dx dt 0 equal 0, or we have the double derivative you can't do anything with. But we have ICs, and this could be 0, or we can have we could just have a derivative again of 1 and make it more complicated of 0, and we can get rid of that. We need two boundary conditions to actually solve something. Now, why is that important? If you go back over here, that's what's happening over here. Think about it. That's what's happening. Literally, what the professor is doing, in my opinion, he just basically hand waved it a little bit. But all of this is probably main constant and all this is probably blah blah blah. In a process, basically, what it's doing is kind of like that format. I'm not sure if it's correct, which is why it's a little weird. But that's what my brain is thinking of when I thought of this. So that's how I've justified his work, justified his textbook's like claim of and from his textbook. I don't really know, but he just jumps into here and just like, no, okay, fair enough. I have to justify it, right? So here's my justification for it. There's probably other textbooks that help you, but like it is pretty it doesn't justify that. It just goes like this. Yeah, so that's what my justification brain is saying. That is probably why it works. So I see. Or boundary conditions is where my brain turned to seek help and figure it out. Okay, so that's great. So next, we're going to go to FE exams questions and where we left off because multiple choice. Oh, 4-year series. I am not going to remember how to do that. That's that's interesting how I left off in one of the hardest parts. I'm going to have to look it up. Um, you're going to have to look up cosine and sine and all this stuff. Usually there's a few ways to do it. The best way to do it is actually just imaginary and cut the shortcut. But yeah, usually I just don't remember how to do it. So I'm going to always have to look it up. I mean, I used to know it. I took the class for it, but I mean, yeah. So. Well, let me look at this. So this is like, what is this? This is like repeating this way. Can we say that as a repeating? Well, it's probably gonna repeat like this, right? So it's not symmetric, right? It's not symmetric, or it's not and it's probably not. Yeah, it's not. Yeah, it's not. What's it again? Odd. So there probably is a shortcut. I'm having a hard time believing that the makers of this question didn't put a shortcut in here because if you don't know, ft equal a, I think yeah, I'm just gonna look it up. Plus summation n equal 1 an cosine omega t plus bn sine omega t parentheses parentheses. You see that? And that's the equation. We're doing it, but I have a hard time believing that there isn't a shortcut for this question because there's no way they want you to solve that question in actuality. Okay. Oh, I'm wrong. Apparently the way to solve it is awesome. Oh, wait. I am a moron. All right, here's what we're gonna do. We're gonna shift this down over here to make it odd. But huh. Yeah. Which means C and D cannot be the answer because you need to increase it by half. So it's either A or B. Now, how do you solve that as a question? Okay, so with that said, I have to look up the odd and even versions of that. So where's odd and even versions? Okay, here's odd and even. So we're not using this one. Actually we are, but we're not using the even version. So get rid of that. We're only using the odd version. So odd version Bn equals 1 divided by t, well, 2 divided by t, right? Equals 0 t by the function t sine and omega t parentheses in dt, right? But here's the thing about this. I cannot claim, I mean, I could put the ft in. The ft would be a linear line, basically. And it wouldn't, hmm, yeah. Um, oh, here's a trick. You don't have to do any of this. Well, Yeah, I just figured it out. The trick is, look at pi. All right, we figure out pi. We have 2 pi over here, 2 pi over here, and the 6 pi over here, and grab a calculator that I don't know where I placed. Got my calculator. And over here, we just have to clear all this, whatever that is. We have to, so when this pi is, when it's sign, right, is 0, right? So is 0, wait, that that would imply that the answer is, no, that's correct. So this is 2 pi, it's 4 pi, and 6 pi, right? So when we reorder this whole thing, we don't need to do any of the fancy calculus. Just swap that away for a second. We don't need any of that fancy nonsensical calculus. You see it too, right? So what we're gonna do is basically make it in the middle because we already know that if the half goes away, it's gonna be half. So we're gonna do this, and we're gonna do it this way. Now, by doing it this way, you know this has to be a half, and this has to be negative a half, right? Wait. Doing half. Uh, wait, this is wrong. Half. Yeah, this is right, negative half. But it has to be like this way. So, and then kind of like that. So we have to get something here. We plug in something like in the middle over here, which is, what is that? That is going to be pi divided by 2 into these equations over here. And by doing so, we can see if it hits 0 or not. And that's how we figure it out. Now, negative cosine, that's pi. Actually, do we even need to do a calculator? I think this is a non-calculator question. I mean, you could use a calculator, but you don't have to. Because this is pi, so that's 1. I already got a bad feeling about that. Because, wait, yeah, pi. Oh, wait. Yeah, it's 1. Yeah. So this is 2 pi, right? And this is 3 pi. That's not getting 0. That's getting 1 or negative 1. And no matter what combination this is, because this is 2 pi, um, it's 2 pi, so it's just basically going, this should be negative, so negative. So that's positive 1, and this is 3 pi, so it's going pi. No, it's negative 1 now because of that negative over here, and then pi, which is positive. So this is definitely not 0. Okay, so over here, with pi divided by 2, this is pi, right? This is 2 pi. This is 3 pi. That's all 0. Therefore, it must be B. There's no doubt in my mind, that's B. Next. So next question is this question. All right, it's clearly the first thing we check if it is either -2 or 2, which is r squared plus 4r plus 4 equals 0, which is 2, which is r plus 2, which equals 0, which means r equals -2. So get out of here A. Yeah, I'm pretty sure that's wrong. So the next question is it, wait, what am I doing? There's boundary conditions here, so let's check if 0 is 1. So if I plug in 0 over here, 0, well, 0, that's a problem, so it must be D. I'll check my answers later, but there's no doubt in my mind it's probably D. Yeah, I show. Next thing over here is the next question, which is another differential equation, which has r squared plus, so -1, so that's imaginary, right? No, that's not right. That's not. Something's wrong. Uh, no, it's not perfect square. I'm stupid. Thank you, brain. It doesn't work. So what we have to do is minus plus and minus square root b squared minus 4ac. Dummy. So b is 2, so 2 plus or minus square root of 4 minus 4, which is 8, which is divided by 2, which is 1, which is minus 1 plus or minus. Is it 1i? Yeah, it's 1i. I guess it's I. Um, so it's plus or minus 1i. Okay, so we have this. So it must be D. Like there's no way this is anything else for D because the other ones don't have an answer. If I get a question wrong, I'll double check later. Over here, we begin over here, where we have following question used to initial below. Um, so it's clearly second order, so we can get rid of that one. Now, technically it's linear, so we can get rid of nonlinear. It is not homogeneous, so it's C. It must be C. Yeah, I will double check that later. What is the statement is true? The system defines is unstable. Okay, probably it's unstable. The Complete solution of the equation could be stable actually because that is a damping term. Okay. Actually, it's pretty easy to check if it's stable or not. It's all positive, so it must be stable. So, uh, it's all. What I mean by positive is if you do 10y pi, 2y pi pi. You see how the coefficients are all plus over here, and then this is a negative over here. So this must be stable no matter what. So this is wrong. The complete solution of the equation will be a sum of a complementary solution, a particular solution that is true. The equation may be solved by no because of the y. This is completely wrong. The equation, no, that's just bullshit. So that's B. Okay, these questions are not that bad. Okay. All right. Y double prime. So why am I doing this? It's obviously going to be this one. Probably this one. But I will double check real quick because I'm not getting my pen working. Okay, r squared plus 9r. No, just r equals 0. So r squared equal negative 9. R equals square root of 3 negative 9 3. So 3i basically, plus or minus. So yeah, clearly these the answer for that one. That's a simple question. Now I'm suspicious. Usually these, I mean, yeah, whatever they probably correct. Next one over here is differential equation. So again, let's see if when it's 0 is 3 and so it's B. I'm just gonna stop over here because we can. I mean, I'll do one more question, why not? But it's B.